let's do some specialty circuits. This is kind of fun. We're going to start with, okay, so these are just going to have input and output. There's a resistor here. There's a diode here, and you're going to say, that looks just like that looks just like a half-wave rectifier, except the two are going to be swapped. If we do V in to V out on this guy, okay, this comes up here, 0.7 volts about. And what this does is no matter what I put into V in, okay, it will never produce more than 0.7 volts on the V out on the positive side. Negative side, it can go wherever it wants, but positive side, it's gonna clamp. So a lot of people call this a clamp, single-sided clamp. Okay, well, that's all good and well. We can do the opposite side. This is pretty obvious. If we put it this way, V in to V out, and then we get the opposite clamp. Clamps down here and comes up 0.7 volts that's there. And so what happens is, and this is V in, this is V out, so you can't ever fry something. So these are protection and safety circuits. Okay? We're going to do one more, and I'm just going to leave this here. What happens when I put both of these in parallel? This creates a double-sided clamp. Okay? 0.7 volts on this side becomes a short at negative 0.7 volts on this side, and we end up with a double-sided clamp. And so this is safety. If we were putting this into a circuit that could only handle 1.4 volts worth of shift, then this would be a good option for this. We can also make a slight modification. I'm not going to spend a lot of time on this one. We'll make a slight modification and put a diode here with a voltage source. I think this one's kind of dumb, but what this does for us is it gives us 5 plus, this is 5 volts or whatever you want it to be. And this gives us a voltage clamp that's up here at 5.7 volts now. Okay, it doesn't allow for anything more than that. Now, personally, if I wanted a voltage clamp, I would use a Zener diode. Okay, this is a double-sided clamp, and this is actually really common to use for safety. If we do two Zener diodes pointed at each other, and sizing these resistors, it depends on how much loss you want on there, but you do need a resistor. This is a double-sided clamp as well, where these corner at are VZ, or VZ0, or VZ1, VZ2, plus 0.7. And that 0.7 is because it has to go forward bias through the one diode. So as the current goes through, it's going to be forward bias through this one. But this is going to resist it up until we get there. And so this is a useful circuit. I would use this in particular if I had an analog to digital converter over here that was 0 to 5 volt and I didn't want to fry it. I would just use it as a single-sided clamp, like this. And I would put in a 5.7 volt or so Zener diode coming into this. And that's just going to suck all of the, you put a resistor here. The whole point of the resistor is there should be zero current that goes into your ADC. Okay? And so that Zener diode, what it does is it allows, we need this resistor, and it just shunts all the current through the Zener diode once we hit the high voltage. And it saves your more important piece of equipment. So maybe you want a separate piece of equipment that, if these two guys fry, that you can replace them easily. So this is safety circuitry. So that's it for those. There are a few other specialty circuits, voltage doubler and clamped and DC restore. I think the only thing that I want to point out is the DC block. This has nothing to do with diodes. But if we have an AC plus a DC source going in, and we put it through some kind of capacitor, and we look at V out here. And I'm going to call this V little I and this V big I for the convention. And if we look at V, big O, it should only be equal to VI. And the reason for that, you might need a resistor on this other side. But if you look at these two in combination, that's going to be basically a high pass filter. Kind of. This just doesn't allow any DC to go through it. It allows all the AC, and so your V out here is only going to be equal to the VI. So this is an important concept for the future. So those are some cool circuits of the day. We'll talk about those. There's a few other items that we need to talk about, which are specialty diodes. Schottky barrier diodes, I just want to point out, they're a little bit weaker, but we'll get into the device physics of this in the next chapter, or the previous chapter. But their forward voltage drop ends up being 0.3 to 0.5 volts rather than 0.6 to 0.8 volts. This is for a standard diode, this is for a Schottky barrier diode. And there's a little trick that they take advantage of to do that, but it still works. But the underlying problem is what we have called ohmic contacts that we have to discuss. So ohmic contacts are something that we will be discussing, and actually Schottky barrier diodes take advantage of that. Varactors are kind of interesting. If we reverse bias diodes, and they're the ones that are specialty made for this, and we'll get into the physics of this. If we apply, I'll draw it like this now, and then we'll have the AC down here. If we apply, our VD here and our VD here, what ends up happening if we look at the voltage on this, and I'll do doubles for these, VDD and VDD. I put a resistor here. Okay, what ends up happening with this, it's rather interesting. This will look like a variable capacitor only to VDD little d, just to the small signal. We control the variable, so this is what's going to control the variable of the capacitor. So in reverse bias, we end up with basically two parallel plates inside the diode that can make it look like a variable capacitor. So those are called varactors, or varactor diodes. There are other ways to make variable diodes, but or variable capacitors, but this is probably one of the common ways. And the trick is that this capacitance that's in the diode is there whether we want it to be or not. We can minimize for it, but it's there. Photodiodes, okay? And so you can get a diode that has light coming into it. Hint, this is all diodes. When I was in graduate school, we did a lab, and here's the sun, okay? And we took a straw, we took two straws next to each other that were perfectly lined up. And this one we put a piece of tape, and so when the sun shined down the straw perfectly, this entire area was lit up with sun. It was perfectly white. And then we'd put a diode in the other one, okay? So I put a diode inside this other one, just a regular LED diode. And this produced a voltage from the sun. It's a photodiode. Now, photodiodes themselves are especially sensitive to light, and so they're a little bit special for that. But we were able to measure the sun brightness as it went through the atmosphere. Low in the atmosphere, there's more craft between you and the sun. High in the atmosphere, there's less, and we could measure that over the day. And so you use an op amp to gain it. So that's a specialty diode. One that we're all familiar with is the LED. And so I just want to point out that the LEDs There's a whole bunch of different kinds. In order to make white, we need red, green, and blue. And they're extremely useful, but the forward voltage drop on these can be like around 3 volts. I want you to verify this in lab. What's the forward bias voltage of that diode, of an LED? This isn't necessarily a specialty, but we'll get into their opto-isolator. And this is, so you take a chip. Inside the chip to one side there's a diode. Okay? On the other side is what we call a phototransistor. Okay? And what this does is it allows us for a completely independent of voltage transfer of a signal from one side to the other using optical. So this inside the chip, it's all sealed off that we can't see it, but this LED lights up that affects this phototransistor, and it makes these two sides act like shorts. Okay? And so that's kind of important for us to be able to use these as separate voltages. So we have voltage over here. This is maybe noisy over here, and we want that noise to not transfer through electrically. And this means that the only thing that can transfer through is light. It also means that we can have AC on this side and DC on this side, or we can have thousands of volts on this side and tens of volts on this side, and we can control it with that. So the opto-isolator is a fun one. Anyways, there's lots of different kinds of specialty diodes. One that you think of as a pulse ox, that I think of as a pulse ox. And when you go to the hospital, they take your finger, okay, and they put a little Band-Aid on it. And on this side, there are 2 LEDs of 2 different red wavelengths. And over here are 2 different photosensors. I don't know what that was. There are 2 different photosensors that are over here. And what it does is it transmits 2 different wavelengths of light through your finger. And depending on the ratio of the transmission of those 2, then it tells you what your blood oxygen saturation is. It's really simple if you think about it. It's just the ratio of what this gets versus what this gets, and then you're just turning on LEDs on this side. All you have to know is the ratio. It's so darn simple, and we don't have to do a lot of math for that one. And they probably charge you $1,000 to put one of those things on your finger. Not that much, but they probably charge you a lot to put one of these plastic things on there. It's 2 photosensors and 2 LEDs. We can put other colors through. What they used to do in the military is they'd send up their pilots, and the pilots, when we only had one color, they realized that, if you're pink, you're oxygenated. Okay, and if you've ever seen somebody that's dusky because they've stopped breathing, or a baby that's stopped breathing, or whatever, they turn gray. It's not really a blue; it's a gray. But with the pilots, so we've known this for a long time. What they would do is they would put just a single LED, or it wasn't an LED, it was just a red light on their earlobe. But to make sure that they had the right transmission path, they would squeeze all of the blood out of the earlobe. They'd just sit there and squeeze the blood out, and then to give them a baseline. And then they compare the baseline transmission for one color to whatever's going through here now. So they did this for pilots back in the World War II era. And that eventually brought in this kind of stuff where we do 2 of these. And you can buy a pulse ox for your finger for $50 now. Does the entire thing, makes nice waveforms, has a little OLED screen on there. OLEDs, organic LEDs, same kind of thing, but instead of silicon, they're using some kind of organic substance like oil, okay, to make OLEDs. So OLED displays are coming up more and more now too. OLED TVs. So this is all stuff you should keep in touch with, because this has been a wave of the future. Probably one of the biggest breakthroughs of the 20th century was LEDs, and where we're taking it now with the 21st century is absolutely incredible. So lots of specialty stuff out there.